The world looks wonderfully dependable when seen from a human distance. A table sits still, a cup of tea gives off warmth, and reality appears to be made of objects with clear edges. But beneath that familiar surface, the ordinary rules completely change, giving way to a restless, abstract quantum reality. For centuries, the universe seemed to follow clean, confident rules. Gravity pulled an apple toward the ground, and electromagnetic waves carried light smoothly through space. Reality behaved like a great, predictable clockwork system, flowing in continuous, unbroken lines that our human senses are built to understand. This neat, sensible picture worked beautifully right up until the late 19th century. The moment physicists looked too closely at something as ordinary as the light coming from a heated object, the smooth old rules began to fail. If you enjoy these calm explorations of the universe, liking the video and subscribing to the channel is a lovely way to help keep these quiet journeys possible as we drift deeper into quantum physics. The trouble started with hot metal. As a piece of solid iron heats up in a blacksmith's forge, it glows dull red, and then yellow, then a fierce white. Physicists tried to explain the pattern of this emitted light using classical equations. This graph illustrates the failure of those equations. The mathematics suggested that as the frequency of radiation increased, the energy pouring out of a hot object should surge upward without any limit. According to this classical prediction, an ordinary oven should emit an impossible, catastrophic flood of high-frequency ultraviolet radiation. Real objects, thankfully, do not destroy the surrounding room with infinite radiation. The physical world behaves calmly. The catastrophe belonged entirely to the theory, serving as a clear warning sign that reality, at its deepest levels, is not smooth. In 1900, a careful physicist named Max Planck stepped into this problem. He was simply trying to find a mathematical rule that accurately matched the true observed radiation curve of glowing objects. To make the mathematics work, Planck had to propose a radical solution. The energy exchanged by matter and light could not flow like an infinitely adjustable ramp. Instead, it was restricted to tiny, strictly allowed portions. He called these distinct packets quanta. The reason no one notices this while boiling water or warming their hands by a fire is a matter of scale. The steps are so incredibly tiny that from an everyday human distance, they blur together to create the illusion of a continuous ramp. The familiar glow of heat looks like a perfectly smooth gradient, but hidden inside it is a precise, granular structure governed by strict mathematical boundaries. 5 years later, Albert Einstein took Planck's strange mathematical fix and treated it as a literal description of nature to explain another stubborn mystery, the photoelectric effect. Einstein proposed that light, the same light streaming continuously through our windows, does not actually behave as an uninterrupted wave. Its energy arrives in individual, separated packets, known today as photons. Classical wave theory suggested that shining a bright enough light onto a metal surface would eventually shake electrons loose, but experiments showed that a massive flood of low-frequency red light would fail completely to eject a single electron, no matter how intense it became. Yet a faint beam of high-frequency violet light would knock an electron out of the metal almost immediately. Each individual electron needed one concentrated, sufficient portion of energy from a single photon to escape. Light refuses to behave like a flexible fluid. It operates as a strict quantum interaction, where nature only accepts exact, indivisible portions of energy. This granular rulebook extends far beyond light. According to classical electromagnetism, negatively charged electrons orbiting a nucleus should continuously lose energy, spiral inward, and crash into the center, meaning stable matter shouldn't exist at all. Physicist Niels Bohr offered a strange answer. He suggested that electrons do not orbit freely like miniature planets in a solar system. They are strictly confined to permitted energy states. By enforcing these allowed states, the atom stabilizes. An electron does not slide smoothly inward. It drops or rises between specific energy levels in discrete, instantaneous jumps. These permitted states also explain why the table you sit at and the blanket you hold actually feel solid. The answer lies in a rule known as the Pauli exclusion principle. This principle dictates no two identical electrons can occupy the exact same quantum state. When atoms get too close, their electron clouds cannot simply merge or pass through one another. The solidity of stone or wood does not come from tiny hard bricks packed tightly together with no gaps. Pressing your hand against a table is simply experiencing the physical pushback of a quantum restriction. Nature also permits deliberate shortcuts through these boundaries. In classical physics, an object without enough energy to cross a barrier will simply bounce back. But a quantum particle is described by a wave function. When it encounters a barrier, its probability wave can extend through the wall, allowing the particle to pass through a barrier it classically cannot cross, a process called quantum tunneling. Deep inside the sun's core, positively charged protons repel each other with immense electrical force. Even at extreme temperatures, classical physics states that these protons lack the energy to push past this repulsion to fuse together. Because these protons behave as wave-like probabilities, a tiny fraction of them manage to bleed past that electrical boundary. They tunnel straight through the repulsion, allowing the strong nuclear force to catch them, triggering nuclear fusion. The sunlight reaching your skin, the weather moving through our atmosphere, and nearly all life on Earth trace their existence back to this microscopic exception. The universe sustains us by permitting an impossible shortcut. Our quiet walk through the hidden structure of reality is only halfway complete. There is much more waiting to be uncovered. We are used to a world that feels incredibly dependable. A table holds its shape, a stone feels heavy, and it is comforting to imagine that zoomed in, this solidity is made of tinier, harder stones, microscopic beads packed tightly together. But that familiar picture is an illusion. In the 1920s, the physicist Louis de Broglie proposed something deeply uncomfortable for classical science. He suggested that matter itself, the very stuff building that stone, also possesses the properties of a wave. When you fire individual electrons through two narrow slits toward a detector, they do not behave like miniature pellets clattering through one opening or the other. Instead, as each solitary electron lands, the overall pattern they build up over time forms bands. This is interference, a classic signature of waves overlapping, reinforcing, and canceling each other out. But these are not physical ripples sloshing through the air like water in a pond. The waves we are talking about are mathematical. They are described by a wave function, which maps the exact probabilities of where a particle might be found when we finally measure it. The Austrian physicist Erwin Schrödinger developed the famous equation that predicts exactly how these strange, wave-like probabilities evolve over time. Beneath the dependable, solid surface of everyday life, matter is not made of simple little objects. It is built from delicate mathematical structures of measurable possibility. Werner Heisenberg revealed another hidden constraint to this quantum architecture. He showed that you can never perfectly pin down both the exact position and the exact momentum of a quantum object at the same time. This occurs not because our microscopes are too clumsy, or because the act of looking gently nudges the particle. The limitation is written into the mathematics. The universe simply refuses to allow both properties to be simultaneously sharp. And that loss of precision leads to an even stranger loss of isolation through a phenomenon known as quantum entanglement. When two quantum systems interact, they can share a single mathematical state. Measure one of these systems, and you instantly know the corresponding result for the other, regardless of how much distance sits between them. You can no longer describe the parts as independent things, carrying their own private properties. This idea deeply troubled Albert Einstein. He famously rejected the notion of this spooky action at a distance, expecting the universe to retain local, separate histories for every object. Yet repeated experiments have shown that nature truly operates this way. At its deepest level, reality is not a collection of isolated things, but an interconnected web of shared states. All of this raises a rather polite but urgent question. If reality is woven from probability and wave-like connections, why doesn't an ordinary wooden chair blur into a superposition of multiple locations? Why does the world look so utterly settled? The answer lies in a process called decoherence. A delicate quantum state can survive when it is perfectly isolated, but the moment it interacts with the outside world, information about its state begins to leak out into the surroundings. The universe is incredibly nosy.
An object sitting in a room is constantly bombarded by stray photons of light, thermal vibrations, and restless air molecules. Each tiny collision carries away a fraction of quantum information. Some physicists describe this through quantum Darwinism. The environment selects the most stable, robust properties of an object and makes countless copies of that information, scattering it everywhere. Because every observer intercepts the same copied data, we all agree on where the chair is. The ordinary, dependable world you experience every day is simply what quantum physics looks like when it is relentlessly observed by its own environment. If the idea of solid, independent matter has been completely dismantled, we are left trying to figure out what particles actually are in the first place. Quantum field theory provides the ultimate foundation. It suggests that the universe is not an empty box containing tiny objects, but rather a space permeated by underlying fields that extend infinitely in every direction. What we call an electron or a photon is not a permanent fixture. It is merely a temporary excitation, a localized vibration rippling through its respective field, much like a single audible note played on a vast invisible string. Figures like Richard Feynman were instrumental in developing the precise mathematics needed to map how these fields interact and exchange energy with one another. This abstract framework is tested and proven by machines that accelerate protons to enormous energies and map the resulting field interactions with staggering precision. Solid matter, in the way our human senses perceive it, is an illusion. It is just the macroscopic feeling of highly stable, deeply ordered patterns vibrating through quantum fields. Yet for all this magnificent precision, modern physics remains fractured. Our two most successful frameworks, quantum mechanics for the incredibly small and general relativity for the incredibly massive, refuse to cleanly integrate. In extreme environments, like the crushing centers of black holes or the very birth of the universe, both theories must apply at once. The search for a unified theory of quantum gravity remains one of the great open frontiers of human knowledge, and the mathematics continue to stretch human imagination. Hugh Everett's many worlds interpretation suggests that every possible outcome of a quantum measurement is physically realized, splitting reality into a near infinite array of separate, non-interfering branches. But there is no need to hold all of that complexity tightly at once. You can still sit in a quiet room, watch the steam rise from a cup of tea, and trust the stability of the wood beneath your hand. The equations work flawlessly. Our technologies function perfectly. But knowing the mathematical rules that govern reality with breathtaking accuracy is not always the same thing as understanding what reality ultimately is. Thank you truly for stepping out of the ordinary scale of things and watching this journey all the way to the end. Every little bit of support keeps these long, quiet explorations alive. If this voyage beneath reality resonated with you, please leave a like on this video, share your thoughts in the comments, and subscribe to the channel for more deep cosmic dives at regular intervals.